Uh, Hello everyone. This is Neng Lu from StreamNative. Today I'm going to talk about Ursa, which is a new streaming engine that's designed to integrate Apache Kafka style streaming directly with data lakehouse architectures. So we developed the new system Ursa here at StreamNative, and also we published a VLDB 2025 paper based on the work we have done based for Ursa systems, and it actually has been awarded as the best paper in the industrial check, which is a great honor. And Ursa introduces a leaderless cloud-native architecture that eliminates many of the inefficiencies for traditional Kafka deployments and integration with lakehouses. So in the following about 20 minutes, I'm going to explain the motivation behind Ursa, its key technical contributions, some of the key components, and how it achieves high performance at a fraction of the cost of existing systems. Um, before we dive into the detailed design of the Ursa systems, I think it's good for us to have some kind of a sense of view on the evolving data landscape. So based on our observations, we're seeing that enterprises are now dealing with massive data streams from IoT sensors in connected vehicles to user log data. And in this kind of environment, the customers or the users can actually not wait for hours or days to get the insights from these data. They need timely analytics, and the teams started to shift from batch only to hybrid streaming and batch methods. So the traditional like batch-oriented ETL pipelines, like using the connectors and other custom jobs, are getting more and more complicated and cost more money. And as the data source becoming more and more, and the data volumes increases, so it will quickly become the bottlenecks for the large corporations, organizations to further scale their workloads. And I think on this graph, this is some kind of typical setups nowadays people are using for like streaming the data and then like moving the data into lake houses. So we can see that there is a Kafka clusters sits in front, and all your applications actually like publishing the real-time data into the Kafka clusters. And then on the back end, there would be like connectors or customer jobs launched to continuously reading from the brokers and sending the data into like different destinations for lakehouse systems. So there are actually a lot of like inefficiencies here if we examine closely. So first of all, there for your like applications publishing data to Kafka, there will be a concept of the leader broker, which is responsible for accepting the data for certain like topic partitions. If your application unfortunately like sits in a different zone to the leader brokers, then there will be incur inter-zone like data transfer when the data gets published. And then like once the data landing in Kafka, because of the Kafka existing Kafka's design, uh, the disk-based replication mechanism, you actually have to copy the data to different brokers in different AZs, and also like you have to reserve some kind of disk in order to host all these data. And because like the brokers like is both responsible for compute and storage, if like some of this storage space is not enough or some of the CPU load is high, you will have to add in more and compute nodes into the system clusters. And most of the time, like for these type of like operations, you will need to do like a partition rebalancing. This may incur actually like impact your SLAs for the cluster service. Um, and some teams we know, like operating a large scale Kafka services, right? They would actually introduce multiple Kafka clusters and add a proxy layers on top of these Kafka clusters to do some kind of seamless switch. But these are all kind of additional like extra operational cost to your service, right? And then like there will be the connectors on the fourth step. That's running connector itself is costly. And since connector essentially are also like applications reading from the Kafka service, it will also hit the inter-AZ like network traffic issues. And once the data like connector sends the data to different lakehouse systems, then we might see like duplicate data copies. So these are the kind of all the like complex and extra costs incurred by these kind of traditional design. So, uh, so upon like observing these challenges and the data landscape shifting, we kind of started to think about what we can do to design a new system. And the design goals are kind of clearly defined before we even like think about how should be. So we want this new system to be very cost efficient, that can drastically reduce the cloud infrastructure cost of streaming data ingestion for the users. And the things now, the data area now shifts towards the Lakehouse architecture. We want this new engine to be Lakehouse-native, that once the data is persisted, it's actually written in the open table formats like the Delta Lake or Iceberg tables. And because we are serving like some of the big customers in different industries, we want, and the traffic load is kind of pretty big. So we want this solution to be both scalable and elastic, so that we can serve those high traffic throughput need, and by decoupling the storage from the compute to allow independent scaling and without any downtime or impacting the SLAs. And the last thing is a little bit kind of explore the new ideas. We want to like have the stream and table duality so that we can merge the real-time event streams and batch analytics on one data set. So with these kind of design goals in mind and the challenges we've seen before, we kind of architectured Ursa in the following like high level in the following graph. So there are multiple layers in our Ursa engine which is responsible for different things. So on the front, it has a Kafka API compatibility layers, for which like all the existing Kafka clients can actually stream data to the engine using the Kafka APIs without any change. This can help minimize the kind of the migration application or client-side migration cost. And for the serving layer, for the brokers, we intentionally make it stateless as well as leaderless, so that like there won't be like any like inter-AZ data transfer cost when the consumer producer applications produce or consume data via the brokers. And in order to back all these brokers, we would have a storage layer, which we designed to be a Lakehouse native storage, so that like one copy of the data can be consumed as a Kafka topic or can be consumed as an Iceberg table. And the interesting part here is like the storage engine can actually be pluggable. So for many of the use cases that's very cost sensitive and want to optimize the cost, you can use cloud object storage like AWS3 as a media. But for some cases, you may want to have low latency support. Then the Apache Bookkeeper can be the media for serving all these Red Hat log object. And to facilitate some of the like data analytics and the Lakehouse queries, we also added the catalog integrations, so that the data streamed to the system can be discovered instantly and governed like in a uniformed way with other data assets the customers have. So this is a kind of very high level overview of the different layers, and we will dig into more details for some of the key components and the implementation details in the following. So for key components, actually, there are three major key components here. The first and the most important one probably is the metadata service, which acts as the central coordinator holding all these metadata information, including like topic partition management information, cluster membership, and offset index, etc. So we built out this metadata service based on a project also developed here at StreamNative called Oxshare, which I believe it would be like a open source. It's already open source, and in the following would be contributed to Linux foundations in the following. And then like on the storage layer, we have the combination of right-hand log and Lakehouse format. So the incoming messages are first appended to a right-hand log on durable storage for high throughput and low latency purpose, and then would be compacted into Lakehouse tables for easy to query and support for the Lakehouse format. So and then we have this stateless brokers, which is like interacting with both the data metadata service and the stream storage to persistent data and get confirmation of all these input offset for the messages published by applications. So this sync service that can speak the Kafka protocol and handle client requests, but they don't like store any data locally on disk. And For the stream format, actually, like once the data was actually published via the Kafka API, it will first write as a raw object. And as the time goes by, there will be a compaction service work diligently on the backend to compact multiple like raw objects and convert them into Parquet format and organize them in the Lakehouse systems for different usages. So for the index part, which is saved in the metadata service, we designed this structure where combined with the index key and the values. So for the index key, it contains like the stream ID, and which is used to identify a topic partition, and then offset end, which is an exclusive upper bound offset, and then the cumulative size to count the total bytes so far. And for the values, there are also like several different components here. First of all, it's the location where the data is stored, whether that's in a WAR file or that's in a Parquet file. And then the file type, whether these entries are saved as the WAR or as a the Parquet object. And we also have like entry count and message count offset in the object and the entry offsets to help like better locate each entries and find the necessary records if the client requests. So now that we are aware of how the data stream format and what's the index looks like, then we can look into like the read and the write passes for the client to interact with the Ursa systems. So to append entries to Ursa stream, so there are five like major like steps. First of all, the entry would be buffered at the broker using the Ursa library. So it will buffers the incoming entries from different writes in memory until some kind of a sizing or like time threshold is reached. Once this kind of threshold is reached, we consider that the WAR object is ready to be flashed, and the library would flash the buffer to WAR storage layers. That's either object storage if you want to minimize the cost, or that's Apache Bookkeeper if you want to have a lower latency. And once the data is persisted in the storage layer, so we will request, the broker would actually submit a request to the metadata service to invoke a transaction update in the service to assign like new offsets and the corresponding index entries. So once the metadata service like confirmed and updated the index, it will return to the broker, and the broker then will act back to the writers. So the write protocol requires this metadata service with either built-in atomic increment primitive or transaction updates to ensure atomicity for offset generation and offset index update. Then, like once the data entry was added, right, we can also read the entries from the Ursa stream using the Kafka API. So first of all, the broker, upon receiving the request, it will actually query the metadata service to locate the smallest index key for which offset end is greater than the request offset. And based on the information returned by the metadata service, the broker would actually read the data from the appropriate offset within either the WAR object or the compacted object based on the where it's located from the index key information we get. And the Ursa reader actually reads the cache data entries from either WAR buffer or read cache to reduce IO amplifications. So this is some kind of the optimizations we did to improve the system performance. And since Parquet format, it's a columnar storage-based format. So if the data is actually in a Parquet file, Ursa would actually need to convert it from columnar to row-based format and then send back to the reader. I think in real-world cases, this is not quite often, and mostly like once the data is compacted and sent into a lakehouse with the Parquet format, people would mostly consume that from using their data lakehouse like tools. And there's also some kind of a niche small details like how the brokers was discovered. Brokers are like zone aware and leaders design. So each broker will advertise its own AZ, which they get this information from Kubernetes or EC2 metadata in Oxia, and it forms a cluster-wide like map from broker to zone cached by every node. Broker hashes all the topic partition zone to pick a zone owner, and in the same AZ serve that partition. And there would also like the partition assignment and the group coordinator assignment to ensure that the cache was hit and we can get a preferred broker in the consumer's AZ. And this is another like some kind of optimizations for local write buffer and distributed read cache to in order to like improve the performance of the tail reads as well as the catch-up reads. So I will just quickly go through that. So there's a magic part, or the another important part is actually the conversion or compaction from the WAR objects to the Parquet like Lakehouse format. So the problem with WAR objects is like it's actually interleaving many streams in one object in order to enable high throughput and low latency appends. But this is actually not ideal for the catch-up reads. So for some of the kind of the fragmented accesses, when the lagging consumer when lagging consumer issues like numerous like non-contiguous range reads across many WAR objects, this would actually for every batch that belongs to its stream, this actually make the read very inefficient. And also if objects, this also fragmented access also defeats like the object store read ahead and the cache localities. So when multiple like consumers backfill different partitions, this application would be compounds. So we designed this compaction service in order to mitigate the issue, and the implementation is roughly like divided into three like steps. So first of all, there will be a leader node, which is inspecting the offset ranges for each of the stream and partitions them into smaller independent processable segments. And once the leader generates those tasks, worker nodes actually would retrieve the designated WAR objects and filter or pre-processing them, and then convert the rule-based data into column of Parquet files. And then once the leader gathers this data, metadata from the workers and the batches, then it will update all these offsets into the index in the metadata service. So that's why we will see that for the index values, some of them are written in the red hat log object type, some of them are Parquet types. And this actually introduces the concept of like stream table like duality. So for a stream like backed by the table, we call, or like in Ursa's perspective, we call that internal table. And also like stream delivered to table, in Ursa's perspective, we call that kind of external tables. So for external tables, it's actually at the bottom on this screen. We will see that the WAR object, the WAR object is still closely sits with the Ursa object. Once the data compacted, it will be sent to the Lakehouse provider and stored in that like object store, and can be discovered via catalog service. And for internal tables, this compacted object is still managed by Ursa. And some of the characteristics is also listed here, like all these Parquet files, even though it is an internal table, all these Parquet files are exposed as a Lakehouse table, and data can be streaming back read from Lakehouse tables with the Kafka protocol. The lifecycle is still fully managed by Ursa, and it's kind of append only. And on the contrary, like for external tables, it can be appended or upserved to the Lakehouse table, but the lifecycle, once the data is streaming out of the Ursa systems and saved in the Lakehouse, the lifecycle is no longer managed by Ursa, and the data that's appended or upserted cannot read back from table using the Kafka protocol anymore. It's more like a typical the traditional like connector approach to sending the data from Kafka out into other destinations. This is like some kind of the architecture we call like Streaming-Augmented Lakehouse, that we put Ursa in between on top of the Lakehouse engine, so that like your external data sources can publish the data using Stream and sending some data, saving the data into Lakehouses, and then the downstream services can be still like consume the data with Kafka format, or like for other like SaaS or BI tools, they can still consume that using the Lakehouse integrations. So this is some kind of we did some kind of benchmark testing, and the cost saving is very obvious compared to like some of the Kafka workloads. And if you're interested, you can check out the blogs we publish here, which is also verified by some of the major data vendors in the industry. And I also added a link for the VLDB papers if you're interested. And if you want to learn more about data streaming and Lakehouse and AI and how they can be integrated or coordinated together, please check out the data streaming summit we have for at the end of this month. And you can use this VIP code StarRocks to get some additional discount. Yeah.
All
Thank
right,
you.
thank you for that, Neng. Now, if we have any questions, feel free to drop them in the Q&A tab that's there on the right. And then we'll take any questions that you have. If you haven't already, scan the QR code in the center for joining the StarRocks community Slack. And if you haven't already, please answer the poll question for the feedback if you have feedback on the session itself. But otherwise, we still have like a couple minutes if there are any